Might our universe not be real? What if everything around you, your home, your car, your city, is unreal? What if it's
just some kind of computer simulation?
You can relax now. Scientists are going to find out. First of all, what does real mean? One of the definitions is when an object, say your car, has some definite properties that don't depend on measurement or observation. It means that the universe exists external to our minds. For example, your car will have 4 wheels even when you're not looking at it. This is something we call local realism. But if we take into consideration quantum mechanics, everything gets a bit dicey. Apparently, several theoretical physicists might have proven that the local realism view on the universe is likely to be false. I mean, what? According to the scientists' findings, the universe can't be locally real because particles can't have definite properties prior to their measurement or observation. It means that the simple process of observing a particle can change its state, which, as you see, contradicts the principles of local realism. In short, the universe is only real when you're looking at it. The conducted experiments demonstrated that 2 particles, regardless of the distance between them, might still remain connected. This concept is known as non-locality, and according to it, 2 particles can travel as far as to different ends of the observable universe and still remain linked, behaving like a single unit. Interestingly, this idea contradicts Einstein's theory of relativity, and in theory, it makes the universe random. But it's still unclear why it happens and what we can do with it. Another idea connected to the unrealness of the universe is that it's just a simulation. But who or what could have created this simulation? There's 3 possibilities: that we're unlikely a simulation, that almost no technologically mature civilization would be interested in running a computer simulation of minds like we have, or that we're almost certainly a simulation. Some experts think that all 3 possibilities could be equally possible. But if the first 2 were false, then the third one would have to be true. Maybe our descendants from a very distant future would be able to run a super complex computer simulation. And then there could be millions of virtual universes with billions of simulated brains in them. However, doubts about the reality of the world around us aren't the only scary thing known to people. Let's talk about the theory of the Great Filter. If you get to think about it, the universe has to be filled with countless life forms. But people haven't stumbled across any of them so far. According to one of the theories, somewhere out there is a great filter. The main purpose of this filter is to stop and finish those civilizations that advance to the level of star colonization. If we suppose that this idea is true, there are 3 possible scenarios for our civilization. A. We're unique because we've passed the Great Filter. Other civilizations haven't managed to do this. B. We're among the first potential colonizers. Before, the conditions in space were too harsh for life forms to leave their home planets. In this case, chances are high that we'll soon encounter other space civilizations. C. We haven't reached the level of technological development that is advanced enough for the filter to locate us. This means that we haven't passed the filter yet. Consequently, the trial is still ahead of us. Then, there's the false vacuum theory. It claims that our universe exists in a false phase state, which means that it's just a temporary thing. What's more, it's only a part of a larger universe. If you compare this large universe with a kettle full of boiling water, the universe we live in will be just a tiny bubble on the surface of the water. But this can't keep going endlessly. One day, perhaps in billions of years, this false vacuum will burst. And then the visible universe around us will instantly vanish with a pop. There won't be any preliminary warning, and we'll have to somehow deal with it.
13.8 billion years ago, a mysterious explosion happened in space. It was chaos, a time when the stars, planets, asteroids, the rest of the space bodies, and galaxies were born. It was the Big Bang, a theory we all know about. But no one knows for sure what happened, where the universe came from, and what was there before. Some even think the universe went through a cycle where it contracted and expanded several times. In 1991, a cosmologist from Stanford University named Andre Linde had submitted an article with the main idea that there was a possibility the universe had been created in a laboratory. His theory said there was a chance an advanced civilization somewhere out there had created our universe. This civilization has made an entirely new cosmos that later evolved its own planets, stars, and intelligent forms of life. 30 years later, many scientists take this theory pretty seriously. They even started talking about things that we, as a civilization, can do to get to such an advanced level. The theory says this advanced civilization decided to add technology that helped to create a new universe out of nothing. It happened through quantum tunneling. It's when an atom can appear on the opposite side of some barrier, even though it's supposed to be impossible, considering the laws of physics of our world. Like if you wanted to pass a tall wall, but you can't pass it with ladders or go around somewhere. Imagine you can just walk through it like a ghost. In our world, it's not possible, but a more advanced civilization perhaps can do it. Plus, they realized how they could create new universes. Right now, on the cosmic scale, we could be a Class C civilization. We don't know how to recreate some things. For example, conditions on the Earth for when our central star, the Sun, goes out. If we manage to become a Class B civilization, we'll learn to adjust conditions to be independent of the Sun. That means we might be able to learn how to live even without it. And if we level up and become Class A, we'll know how to recreate cosmic conditions and produce our own cosmos in our laboratories. We think of the world we live in through 3 dimensions of space: east-west, north-south, and up-down. There's also 1 dimension of time, which means we can distinguish past from future. A 5th dimension would represent 1 more extra dimension of space. The theory of its existence was first mentioned in the 1920s. It was inspired by the theory of gravity by Albert Einstein, who said space-time is warped by matter and energy. We can't perceive these 4 dimensions, but we see how an object moves and attribute it to gravity. And maybe there's some other force, like the electromagnetic force, that's more than 1,000 times stronger than gravity, that could explain things going on in that extra dimension of space. The 5th dimension is curved in a way we can't see it, but the idea about it was mentioned in a string theory. It considers the universe as really small strings of mass energy, not as particles. They vibrate in 10-dimensional space-time, considering 6 dimensions are rolled up way smaller than a single atom. That led to the picture of the universe as a 3D island that floats in 10-dimensional space-time. Also, the 5th dimension might be an excellent explanation to tell us more about dark matter. That's the invisible stuff with a mass, but we can't see it, nor can it interact with ordinary matter. And dark matter is 85% of all the matter in our universe. The universe can't be still. It's constantly in motion, either contracting or expanding. We used to think there were 100 billion galaxies, but it turns out there are more than 1 trillion. The galaxies are moving away from each other. This is what it means when scientists say the universe is expanding all the time. There are voids between galaxies that sometimes stretch millions and millions of light years across. They can seem empty, but they can also contain way more matter than we can find in galaxies. Still, stars usually can't be formed there because the matter between those areas has lower density. But there's still plenty of so-called intergalactic stars. A good example is the Virgo galaxy cluster, 10% of which are intergalactic stars. We don't know how exactly they got there, but there are 2 possible ways. 1. Stars can collide, merge, or pass close to another galaxy, which can kick it off from its parent galaxy. Option number 2. A supermassive black hole can accelerate a star to very high velocities if they have a close encounter, which can, again, make a star be expelled from its parent galaxy. If you could have a giant magnet, you could even pull something out from the vicinity of a black hole. That's possible if the magnetic field near a supermassive black hole is as strong as the black hole's gravitational field. But it doesn't work if we're talking about material that's already beyond the black hole's event horizon. That's a spot with a gravitational force so powerful not even light can get away. You'd need to accelerate this material to the speed of light, at least, to get away. For that, you'd need an infinite amount of energy. But a magnet could help if something's heading toward the black hole but didn't get inside yet. When someone mentions a black hole, you might get a picture of some giant void in space. But the Milky Way is most likely full of thousands of smaller black holes that float around the galaxy. When a star comes to its end, it will destroy itself in a supernova explosion, which is a cataclysm of energy. In that explosion, the densities in the core will reach an intense enough state that nothing will be able to escape. At the same time, the major part of the star explodes outward, but a part of it collapses inward, creating a black hole. The bigger the star, the bigger the hole. The black hole then swallows everything that comes in its way, including other stars as well. When a star gets sucked up into the black hole, it's ripped apart because of the strong gravity inside the black hole. Some of its parts fall into the black hole, while others get ejected at incredibly high speeds. Some black holes might have been formed in a different way. The early stages of our universe were, to say the least, pretty chaotic. It had high temperatures and pressures, and was in a state that shaped the entire cosmos. Under the right conditions, any old gas patch may have shrunk itself to become a black hole. And they came in many different sizes, from something that weighs a couple of pounds to giant masses like thousands of suns, and those in between. They aren't really black. Black holes are areas with strong gravity, and no object can escape when it gets inside. They feed off electromagnetic radiation, such as light and space particles. Since they're consuming matter all the time, black holes give off a dark glow. The Earth is not that close to the inhospitable edge of the solar system. We're the sixth planet from it. Scientists made a pretty cool 3D map of our solar system where we can see what the edge looks like. It took them 13 years to design it. The boundary is called the outer heliosphere. It marks the area in space where the solar wind, which is the stream of charged particles our sun emits, gets deflected and draped back by the radiation coming from the empty region beyond our solar system. The inner layer of the heliosphere is where the sun and the planets have a rough shape of a sphere, while the outer layer is not that symmetrical. This asymmetry happens because our sun is moving through the galaxy and goes through friction with the radiation in front of it. Black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of these dolls has boundaries that we're going to cross. For that, we'll need a spaceship, and a big one. It also has to be able to move 100 times faster than the speed of light. You get on board and start the engines. 62 miles above sea level is our first boundary. That's 10 times higher than passenger planes fly. This point is called the Kármán line. It separates the atmosphere of the Earth from outer space. Now we fly further to the edge of our solar system. We turn on the hyperdrives and fly past Mars, Jupiter, Saturn, Uranus, and Neptune. We've traveled a distance of 100 astronomical units. 1 AU is the distance from Earth to the Sun. And here's the boundary of our solar system, the heliosphere. Here, the speed of the solar wind decreases rapidly. First, it drops from 620,000 miles per hour to the speed of sound. Then, there's a layer called the heliopause. This is where the wind almost vanishes. And then, our ship experiences a bow wave. This is where we feel the force of the interstellar wind, which collides with the boundary of our solar system. When you pass this boundary, you find yourself in the dark of interstellar space. And here, you can find two human-made objects that made this trip for the first time in history. They're Voyager 1 and Voyager 2. Voyager 1 crossed that boundary in 2004. Voyager 2 did it in 2007. These space probes discovered that the heliosphere is not a perfect ball around the sun. Its southern boundary is 10 AUs closer to the star than the northern one. So, we're moving in interstellar space and will soon approach a stone wall around our solar system. 200,000 AUs further, and there it is. This wall of rock is the Oort cloud. In fact, it's a pile of asteroids that surround our world. Scientists speculate that the Oort cloud could be the source of comets and meteorites that fall to Earth, but they're so sparse that we easily fly between them. Now we're in complete darkness. The Milky Way is about 106,000 light-years wide. In a conventional rocket, it would take billions of years to fly across that distance. But you throttle to the max. You masterfully fly past the stars and planets as if on a racetrack. And within minutes, you're at the edge of our galaxy. There's no more interstellar wind. All you see are bright dots somewhere in the distance. These dots are huge galaxies. We need to look at a map to make a route to the edge of our entire universe. You're here, near the Milky Way galaxy. It's part of a cluster of galaxies called the Laniakea supercluster. But even this huge thing is like a little street in a big city. Zooming out, we find Hydra Centaurus supercluster. Thousands of galaxies on the map look like little dots. Maximum zoom out. This is our entire observable universe. We thought it was infinite, but we may have proof that it has a boundary. It's here, 10 billion light years away from our home. Even if you travel at the speed of light, a trip there would take twice as long as our whole planet has existed. During that time, the sun will either fade away or explode like a supernova, destroying our entire solar system. And if you can live that long and then return home, you will see that our galaxy is there no more. It's long since collided with the Andromeda Galaxy and merged into one big cosmic body. Luckily, your ship is able to warp space-time so that this journey will literally take a few seconds. Boom! Congratulations! You've arrived at your destination, the Eridanus supervoid. Some scientists believe this location is the evidence of collisions of our universe with something big enough to leave such a large scar. The Eridanus supervoid is an empty and cold space 1 billion light-years wide. If you think of this void as a cup, it would fit at least 10,000 galaxies, and it appeared after an accident of gigantic proportions. The object that crashed into our universe was another universe. Yes, other universes may actually exist. Imagine that our entire universe is a huge bubble that contains all the clusters of galaxies in the observable universe. There could be an infinite number of such bubbles. They could have been born during the Big Bang. These universes may be different from ours. They may have other galaxies and nebulae. But these bubbles could also be parallel universes. This means that if you chose cereal over oatmeal in the morning, in another universe, your twin would choose the oatmeal. Every choice you ever made in life had completely different consequences in a parallel universe. And because the number of choices are infinite, there's a whole infinity of parallel universes. So, like a regular bubble, our universe has a wall that is near the Eridanus supervoid. Long ago, another bubble flew past ours. As they approached each other, their gravitational fields began to interact. Our boundary wall began to deform and pull toward the other universe. The same thing happened on the other side. Then the walls of our universes came into contact. But as these bubbles moved, their connection began to break, and the other universe just ripped a huge chunk of ours. A cold void was formed at the point of collision, and that was the Eridanus supervoid. The problem is that the universe looks the same to the observer, regardless of point of view. For example, imagine a basketball hanging in the air. Now, if we put an ant on the ball and tell it to find the edge of the ball, it will start running around it, making an infinite number of circles. But the landscape around the ant will not change. All it will see is a rounded horizon. That's because the ball remains the same from any point of view. The same thing happens to us when we try to find the edge of our universe, all because we imagine the world in three-dimensional space, and our view is limited. For example, you see an ordinary square in two-dimensional space, but if you add depth and change the point of view, voila, it's a cube. If we could see the universe in four-dimensional space, a square might be something completely different. But maybe we can leave our home bubble. The key to traveling to another universe might be inside a black hole. A black hole is one of the most mysterious objects in the universe. They're so heavy, they warp not only space, but time as well. It's like putting a heavy boulder on a net. The net will sag, and the closer you get to the boulder, the stronger the curvature is. Once you're in the gravitational field of a black hole, you can't leave it. We still don't know what might actually be in the heart of a black hole. Some scientists speculate that white holes also exist. Theoretically, they should be born along with black holes. Except for the color, they're the exact opposite of black holes. Nothing can come close to a white hole. At the moment, there's no data on such objects, but general relativity theory suggests they do exist. There's also a theory that a black hole may be a passage to another universe. When you get into a black hole, you can come out the other side through the event horizon of the white hole. So you bypass the boundary of the universes and find yourself in a completely different world. But we may have proof that a white hole exists. In 2006, scientists discovered an unusual burst of energy somewhere 1.6 billion light years away from Earth. This burst was unique. It didn't look like a supernova explosion or even the merger of two black holes. Some astronomers believe it was the birth of a white hole. But because it was unstable, it was destroyed almost immediately. This process was reminiscent of the birth of our entire universe, the Big Bang. So, scientists called it the Little Bang.